Start with a rather famous example of, I guess we'd call it a special case of what we're trying to prove. Let's look at sigma of 6, folks. Now, sigma is the sum of the divisors function, the sigma function, and you just sum up the divisors. So in this case, we get 1 plus 2, and you include the number itself, not just the proper divisors. That's why the definition of a perfect number is the way it is. You'll see this equal to 12, which is double 6, and that makes it a perfect number. Okay, not that that's important right now. Okay, now let's take a look at sigma of 7. 7's a prime number, and they're the smallest, if you will, on the sigma side of things because they only have two divisors, namely 1 and 7, which is just the definition of a prime number. So we have this thing that might look odd initially because it proves that sigma is not an increasing function for sure, but 6 is a smaller number, but the sum of its divisors is larger. You know, naively, you might think that larger numbers have more divisors, and so the sum of the divisors of a larger number would be larger than the sum of the divisors of a smaller number. It's not the case, and we do have a counterexample. We do have that example right here, sigma of 6 is strictly greater than sigma 7, and 7 is notably prime. Okay, now that motivates us to try that idea on this general proof. Prove there are an infinite number of integers in such that sigma at n-1 is greater than sigma at n, okay, which, again, this is a general statement for this special case. All right, now, we're going to let n be an odd prime greater than 3, and you'll see as the proof why we need it. 3 doesn't work, nor does 2. The first one that works is 5, and you'll see why when we go through the proof here. We'll choose n to be an odd prime, and I intentionally call it n, not p. A lot of the proofs on this kind of thing, they'll call it p, which is misleading in my opinion. So let n be an odd prime greater than 3. Now here's this is the whole pith of why it works. If n is an odd prime, then n-1 is even, which is true of an odd number too, but you need the prime part for the next part. All right, so if any even number has divisors 1, 2, and n-1, except for 3. You see, if n were 3, the only divisors would be 1 and 2 here. 2 and n-1 would be the same thing. If you go up to 5, they're distinct. That's why it has to be greater than 3. All right. Now, so anyway, I'm just writing down what I just told you. n-1 is even. That means at least it has the divisors 1, 2, and itself, right? So that sums up to n plus 2. So this is greater than or equal to. All right, greater than or equal to. But as we've noted earlier, if n is prime, its only divisors are 1 in itself, so that's n plus 1. So you see, we clearly get, just from this, it's a very clean, simple proof. There's always some smaller primes that are exceptions on these kind of things, it seems like, right? But that's just the way it is. 2's notably an exception, you know. Almost everything, it seems like. But so we get that this is true. And why is it? We prove there's an infinite number. Well, there's an infinite number of primes greater than or equal to 5, right? So that completes the proof. A nice proof. I like it. Now, this is very crude in the sense, normally on this type of number, you're going to have many more divisors than 1, 2, and n-1. So this is very crude, but it still proves what we set out to prove. So I'm going to put QED. Okay, and I hope everybody enjoys the NBA Finals.